So, we know already how crucial soil functions are for sustaining life on Earth, and how soil modeling is essential for soil protection, management and engineering. We now will elaborate a bit more the different steps that are followed when a soil modeling program is developed. Actually, these different steps will also be followed in this class to develop soil models for water transport, solid transport and water transport in groundwater. The first step is the development of a conceptual model. We need to define exactly what we want to model. We need to define the processes, we need to define the spatial and temporal scales, we need to define possible parameters and boundary conditions, and we need to define the possible application of the model. The results of this conceptual model building phase is generally a kind of a diagram, a sketch or a figure, which is a qualitative description of the problem that we are dealing with. An illustration is given here. Suppose we want to develop a model supporting the management of a subsurface pollutant storage facility. We consider that liquid pollutants will be stored in lime barrels, but from an environmental risk point of view, we would like to know what would happen if the barrels would fail and if the liquid freely enters in the storage cave. We therefore would like to know whether the pollutants can migrate and disperse in the environment. Let's focus on the horizontal migration. The problem that we are dealing with is possible liquid transport from a potential wet storage cave into a potential dry soil. We would like to describe this migration in space, hence horizontally, and in time. Given the fact that the soil may be dry, we may expect a gradient of water content between the cave and the soil exists, and hence by capillarity that the liquid diffuse will into the soil. The expected process is therefore a capillarity-driven diffusion process. A model should therefore be able to describe the horizontal diffusion of liquid over a range of some meters, and this for different moments in time, and in terms of the properties of the soil of our storage facility. That's it. We have a conceptual model. We know what processes we want to model. We've defined qualitatively the spatial and temporal scales for which we want to elaborate the model. And we have some idea of parameters and variables that may affect the process of the model. All this is represented textually or graphically in the slide. A conceptual model is useful, extremely useful. It allows to fix ideas. It is a narrative, qualitative, and uses very often graphical formalism to transfer ideas. Conceptual models are therefore excellent tools to communicate about the process you want to model with possible model users. It should also be noted that there does not exist a reference conceptual model for a given problem. The model should be considered as a social construct and therefore as a result of a subjective process that depends on the ideas and perceptions of the model developer and the interaction he has with possible model users. Soil process modeling is therefore inevitably subjective, which means that it depends on the ideas of the model developer at a given moment, but also evolutive, which means that conceptual models may evolve in time. In many disciplines, particularly in human science, the modeling process stops at the conceptual modeling step. In engineering, however, we very often go much more further and aim to translate the qualitative conceptual model into a quantitative numerical tool. A second step in the overall modeling framework may therefore consider the translation of the conceptual qualitative model into a quantitative model. Obviously, we use in this step mathematical formalisms, as mathematics allows us to define and handle variables and parameters in a rigorous and logical way. The problem of the horizontal storage facility, for instance, can be modeled by means of a differential equation that quantifies the possible change of water content across an infinite small soil volume and for an infinite small time step in the neighborhood of the storage facility. In this equation, theta represents water content, x represents the space, and t the time, and d a soil-specific diffusion constant. The use of differential equations is very popular to describe soil hydrodynamic processes, as it allows to integrate the rigorous descriptions of physical processes that drives the hydrodynamics into a conceptual approach. In this case, for instance, we combine a mass balance equation on an infinite small volume with a diffusion equation to infer the presented differential equation. We come back to the development of this equation later on in this class. Yet, it should be reminded that differential equations are not the only mathematical tools that can be used to translate the conceptual model into a mathematical model. In many cases, simple algebraic equations can be used, and in other cases, integral formulations are used. In this class, however, we mainly use differential equations to describe the soil hydrodynamic process. The differential equations formulated in the second step is of little use for practical applications. In the case of the storage facility problem, we are not interested to know the variation of water content locally at an undefined place or time, but we are interested to know the water content and flow at any place in the soil surrounding the storage facility and at any time considered relevant in our conceptual model. This means that we need to solve the differential equations. In mathematical terms, we need to integrate the equation in space and time. Many techniques exist to solve differential equations. Analytical techniques can be developed for simple cases, which means for simple differential equations characterized by simple initial conditions and boundary conditions. In many engineering applications, however, these conditions are not respected, and numerical techniques need to be developed to solve the differential equations. In this class, both analytical and numerical techniques will be used to solve the soil hydrodynamic differential equations. For the pollutant storage facility problem, for instance, an analytical solution is given here. The results of the analytical integration of the differential equation is an explicit and quantitative mathematical formulation of the variable of interest, in this case the water content theta, as a function of time and space, and this in terms of the variable boundary conditions, in terms of a property that is relevant for the soil, which is the parameter d. When the coding of this equation in a spreadsheet or simple calculation program, we can model theta for any x, t, d, theta I, and theta s. We should, of course, in this type of application know the parameter of the model. That means, in case of the storage facility problem, that we should be able to quantify the soil water diffusion parameter d. In many cases, these values cannot be rigorously defined from generic knowledge. Indeed, natural soils are very heterogeneous, which means that the properties vary considerably in space. Hence, the soil properties that drive the soil hydrodynamic process will also be very variable. The soil parameters should therefore be identified for each given application. Many techniques exist to identify model parameters. Some rely on soil sampling and soil characterization in the lab, while others rely on in situ assessments. In this class, we will illustrate some of these techniques, in particular techniques that allow assessing model parameters from in situ observations using so-called model inversion techniques. We suppose that with such techniques, realistic and quantitative values of the model parameters can be obtained. Unfortunately, the model parameterization step is not the final step in a modeling program. Modeling is a subjective and therefore, by definition, subjected to modeling error. The modeling error can be of different origin. Errors can be made in the conceptual model, for instance by omitting the description of a process that is essential for the soil. But modeling error can also be made in the translation of the conceptual model into the differential equation, or in the solution of the differential equation, or in the definition of the initial and boundary condition, or in the identification of the model parameter. So, modeling error is therefore inherent to the modeling process. The modeling process can therefore only be used for management and engineering if this modeling error is under control. That means we need to validate the modeling process. The validation process does not aim to demonstrate that the modeling is valid or not. We know by definition that no model is really completely valid, so that's also the case for soil hydrodynamic models. The validation step rather aims to assess the modeling error and to compare this error with thresholds that are considered appropriate for a given application. We do not want to know whether there is a modeling error. We want to know whether the modeling error is acceptable. There are many ways to validate models. A popular method consists in comparing the results of model predictions with independent observations of the variables that the model is predicting. For instance, take again the case of the pollutant storage facility problem. If we make an experiment in which we allow water to diffuse horizontally in the soil from the wall of the storage facility into the soil, and if we measure the water content at a given moment at different positions in the soil, then we can compare the model with these observations. We can make this comparison graphically, as illustrated in this slide. The model calculated curve is in close agreement with the observation, and this gives us, in this case, confidence that the developed model may be appropriate for the envisaged application. Alternatively, we can calculate indicators of modeling error, such as the sum of square deviation, or the sum of square deviations compared to the total variation, etc. There exist many different modeling error indicators that we can calculate. We will give some examples later on in the class. In the most advanced step, we can even compare this modeling error to expected variation of measurement, the so-called measurement error, and evaluate the modeling error with a statistical test. Following such an approach, the null hypothesis that we test in a statistical frame is that the modeling error equals 0. Once the model is validated, we may be confident that the modeling error is under control and that we can use the model for a given application. The next step is then the use and implementation of the model for hypothetical conditions. Indeed, the strength of the modeling approach relies in the fact that the system can be evaluated for hypothetical conditions for which no observations have been made. In our case, we can make virtual numerical experiments and evaluate how the soil system will react when it is subjected to hypothetical boundary conditions. We can therefore make scenarios and evaluate whether the system is likely to comply with a set of environmental criteria. For instance, in the case of the storage facility, we can evaluate whether the wetting front remains close enough to the storage cave and therefore whether the dispersion of the pollutants remains local. For doing this, we need to define the initial and boundary conditions. Finally, with a defined boundary condition, we can run the model. For instance, in the case of the diffusion model, we can evaluate the water profile as a function of time. We see, for instance, that for 1 hour, the first blue curve, the water remains close to the cave's soil interface, as the infiltration front has not reached yet a distance of 20 centimeters. However, if the time proceeds, then the infiltration front penetrates further in the soil, and the risk of increasing the dispersion of the pollutant increases also. In this class, we will implement such a systematic modeling framework for 3 different essential soil processes. It is the soil water transport process, the soil solid transport process, and the transport of water in the groundwater system. Before starting with developing the conceptual model and mathematical models of the first process, you may reread the text describing this general framework into the syllabus of the course.